When we talk about cell potential, we are actually getting the difference of the potential of your two half cells. So when we measure the potential of an electrochemical cell, that potential is actually the potential difference of your cathode and your anode. Now, it's difficult to precisely measure the potential of a single half cell. And because of this, chemists thought of choosing a reference half cell, or they simply call it reference electrode. Just like the concept of your standard enthalpy of formation, standard free energy of formation, we also have what we call the standard electrode potentials. For these values, so the standard electrode potentials, they were obtained by choosing a reference half cell or a reference electrode. So this is what we call the standard hydrogen electrode or the SHE. So again, this is the chosen reference electrode. And the reason why they chose it is because it has a it's fairly easy to set up this electrode. You simply want to have a solution with a pH of 0, which means the concentration of your hydrogen ions is 1. And you have a glass tube dipped into this solution. And this glass tube is filled with hydrogen gas with a pressure of 1 atmosphere. So after choosing this reference electrode, they assigned this half cell a potential of 0 volts, which means that they can partner any other half cell with this reference electrode. And once they measure the cell potential, again, cell potential is the difference of the potential of your cathode and your anode. Then, if you set this reference electrode as your anode, so you have the measured cell potential, again, it's the difference of the potential of your cathode and anode. And since we are in a standard state, we place the not symbol there. The reference electrode is set as the anode of your electrochemical cell. And because it's assigned a potential of 0, any cell potential you measure with the standard hydrogen electrode as your anode, the measured cell potential will become what we call the standard electrode potential for your cathode. So it means that if I connect another half cell to this standard hydrogen electrode, let's say a copper electrode or a copper 2 plus half cell, and we measure a cell potential of 0.340 volts, it means that I have a standard electrode potential of 0.340 volt for the copper to solid copper electrode. Now, this copper 2 electrode is the cathode, right? So it means it's a reduction reaction taking place in it. These standard electrode potentials are also called standard reduction potentials. So that's represented as E naught red or standard reduction potential. So the standard reduction potential for your copper 2 plus copper electrode is 0.340 volts. Meanwhile, if you connect a zinc 2 plus zinc electrode to your SHE, again, your SHE is the anode and your zinc 2 plus zinc electrode is your cathode, you get a measurement of negative 0.763 volt, which means that the standard reduction potential of your zinc 2 plus zinc electrode is negative 0.763 volt. So we can actually make a list of our standard reduction potentials for any half cell that you can think of. You just need to partner it with your SHE, measure the cell potential, and that value is the standard reduction potential of your cathode. So in electrochemistry, we often use this so-called table of standard reduction potentials. Now, how can this help us in determining standard cell potentials? Well, if you just choose any two half reactions from this table, you can actually combine them. You just choose which of the two will become your anode. Okay. You still use the formula um, cathode minus anode. So you have the standard reduction potential of your cathode reaction minus the standard reduction potential of your anode. Now you might think, isn't it an oxidation reaction that is taking place in the anode? Yes, it's an oxidation reaction. And that's the purpose of your minus sign in the formula. So the minus sign is to invert the sign of your standard reduction potential. So for example, we have this cell. So we have the zinc anode, okay? And we have the copper cathode. Okay, so again, in our anode, we have the zinc solid getting oxidized to zinc ion. So this is in our anode. And then in our cathode, we have your copper 2 ions being reduced to solid copper. So if we look at our table of standard reduction potentials, we see here zinc. So there's your zinc reduction half reaction. And we see here copper reduction half reaction. But again, zinc is being oxidized. So this is not taking place, but the reverse of this reaction. So we will not use negative 0.763. Okay, the reverse of the reaction is taking place. Again, that is the purpose of your minus sign here, to invert the sign of the standard reduction potential of your anode. So how do we get the standard cell potential for this electrochemical cell? So we have the standard reduction potential for the copper electrode, which is positive 0.340 volt minus negative 0.763 volt. So the answer here is so that's 0.340 plus 0.763, and we get 1.103 volts. And according to what we learned, a positive cell potential means that the reaction is spontaneous. So what does this mean? Since we are at standard state, again, the standard state is defined as 1 atmospheric pressure for gases, 1 molar concentration for aqueous solutions. So this means that if you have an electrochemical cell set up like this, and the concentrations of your ions are 1 molar, then you have a cell potential of 1.103 volts, and your reduction or your redox reaction in this electrochemical cell is spontaneous. So this is how we use our standard reduction potential table. Okay, so let's try another problem. So determine the standard cell potential for the redox reaction in which iron 2 is oxidized to iron 3 by permanganate in acidic solution. So if you have already watched the video on how to balance redox reactions, most often you have redox reactions that take place in acidic conditions and redox reactions that take place in basic conditions. So even if you have the same set of reactants, the products will be different if the redox reaction is taking place in acidic conditions and in basic conditions. So most often, it is also important to indicate whether the reaction is acidic or basic. So here we see that the reaction is in acidic solution. So we will focus on the acidic part of our table. So we are looking at the oxidation of iron 2 plus to iron 3 plus. That means in our anode, the reaction is Fe2 plus forming Fe3 plus 1 electron. And in the cathode, our reaction is, of course, the reduction of permanganate. So we have permanganate. Now, if we are not sure what the reaction is, we can always look at our table because the reaction is indicated there. So we see here the reduction of permanganate in acidic solution. So the other reactants are hydrogen ions plus 5 electrons, and the products are manganese 2 ion plus 4 water. So to balance our redox reaction, I will multiply this by 5 so that I get an equal number of electrons for the two half reactions. And let's write the overall redox reaction. I forgot the H plus on the reactant side. Excuse me. Then we have manganese 2 plus 4 water molecules. So this is our balanced redox reaction. Now, how do we get the standard cell potential? Again, it's indicated it's in the standard state. So it means that the concentrations of our ions are 1 molar. So you need to always keep in mind that at standard state, the concentration should be 1 molar. So again, the formula for our standard cell potential is the standard reduction potential of your cathode minus the standard reduction potential of your anode. So our cathode is that of permanganate, so that's positive 1.51. Meanwhile, our anode is that of iron 2 to iron 3. So for us to find this, we need to look for the reverse of this reaction. So that's iron 3 to iron 2. And we have it here. So its reduction potential is positive 0.771. So again, the minus sign here is, its purpose is to reverse the sign of the standard reduction potential in the anode. Because it's in the anode, it should be an oxidation reaction. So this will give us a value of 1.51 minus 0.771. That's positive 0. Excuse me, positive 0.739 volt. Which means this reaction is spontaneous at standard conditions. Let's try another problem. So cadmium is found in small quantities wherever zinc is found. Unlike zinc, which in trace amounts is an essential element, cadmium is an environmental poison. So it's very important to trace cadmium. So to determine cadmium ion concentrations by electrical measurements, we need the standard electrode potential for a cadmium electrode. So we have the following cell. So you have the cadmium electrode as your anode, and you have a copper 2 electrode as your cathode. And you measured its standard cell potential, and you got a value of 0.743 volts. From this, we can determine the standard reduction potential for your cadmium electrode. So again, your cadmium electrode is your anode. So that means your anode reaction is your cadmium solid transforming into cadmium ion plus 2 electrons. And you have your cathode reaction, which is your copper 2 ions becoming solid copper. So there's no need to multiply any coefficient in any half reaction because the number of electrons is equal. So we have the overall redox reaction. So for this redox reaction, the measured standard cell potential is 0.743 volts. So now we use the formula. Standard cell potential is equal to the standard electrode potential of your cathode minus the standard electrode potential of your anode. So the unknown here is that of the anode, right? Because we are looking for the standard electrode potential of the anode. So we have 0.743 volt as the standard cell potential. And from our table, we have positive 0.340 for the standard electrode potential of your copper, which is in the cathode, minus our unknown. So the standard electrode potential for our anode is 0.340 minus 0.743, which is negative 0.403 volt. So this is the standard electrode potential for this cadmium electrode. So for any measurements, other measurements involving cadmium, you can now use this value. Again, this should be in the standard state. The concentrations of your ions should be 1 molar. Okay, so hopefully you appreciated this table of standard reduction potentials. Now let's go to the relationship of electrochemistry and thermodynamics. In particular, the parameter we are looking at, or the thermodynamic quantity we are considering, is the change in Gibbs free energy. So the formula is straightforwardly given. The relationship of electrochemistry, the parameter measured here is cell potential, right? And thermodynamics through the parameter delta G is given by this equation. So we have the change in Gibbs free energy at standard state equal to negative number of electrons times Faraday's constant times your standard cell potential. So N here is the number of electrons coming from your balanced redox reaction. This is often called electron number or charge number, and keep in mind it doesn't have any unit. Okay, so it's simply a number, and this number is the number of electrons in your balanced redox reaction. Faraday's constant, on the other hand, gives us the charge per mole of electrons. So Faraday's constant has a value of 96,485 coulombs per mole. And then you multiply these two by your standard cell potential. So for example, if we have our She here, and the thing is, okay, when we talk about electron number or charge number, because we know that for a chemical reaction, we can actually manipulate the coefficients, right? So for example, we have the She here, the standard hydrogen electrode. Okay, so written as an oxidation reaction. We can also write the reaction in this way. So we divide the whole reaction by 2, and we get new coefficients, which is 1:1:1/2. Now here, I'm going to show you that cell potentials are intensive properties, which means that it doesn't depend on how the stoichiometry of your chemical reaction is written. Okay, it doesn't depend on it depends on the concentration of your reactants, but the number of electrons involved in the redox reaction that doesn't affect the value of your cell potential. And you will see here. Okay. So again, we can write our Xi in two ways. Okay. Both are balanced. The coefficients are just different. Okay. So for example, we coupled this with the copper to copper electrode. So we have our anode half reaction written like this. And we have our cathode half reaction. Okay. So for this one, we see that our overall reaction involves 1 mole of hydrogen gas and 2 moles of hydrogen ions. So if we look at the standard cell potential, this gives a value of 0.340 volts, which means that if we get the standard change in Gibbs free energy by using this formula given, so we have delta G naught is equal to negative NF E naught cell. Okay. So that would be -2 because there are 2 electrons from our balancing times 96,485 coulombs per mole times the standard cell potential 0.340 volts. That will give us a value of negative 65,609.8. So the units are coulomb volt per mole. So recall class that 1 joule is equal to 1 coulomb per 1 volt. 1 volt is equal to 1 joule per coulomb. 1 volt is equal to 1 joule per coulomb, which means if we multiply coulomb and volt, that is equal to joule. So this is also written as negative 65,609.8 joules per mole. And of course, this should be in joules because we are considering a thermodynamic quantity. So we get negative 65,609.8 joules per mole. So this is for this reaction. And if you recall, in our discussion of thermodynamics, it is also possible for us to divide this equation by 2, and we get this balanced reaction. So that's also 1/2, and we get 1 mole of H plus aqueous plus 1/2 mole of solid copper. Now, if this is the delta G naught for this reaction, the delta G naught for this reaction should be half of this. So that should be negative 32,804.9 joules per mole. Now, how does that affect our standard cell potential? So if we consider the reaction in our anode as this one, then our overall reaction will be written like this. Based on our balancing, your electron number is 1. And using our formula for delta G naught, that's negative 1 times 96,485 coulombs per mole. Now we are going to use the same standard cell potential value because I mentioned that it is an intensive property. We should get the same quantity, 32,804.9 joules per mole. So again, the way we balance the redox reaction affects the value of your delta G, because delta G is not an intensive property. But the way we balance our redox reaction doesn't affect the value of our standard cell potential or cell potential in general. So if we balance this reaction involving just one electron, so our electron number is 1, then we get half. We get a delta G that is half of what we computed in the previous consideration, the one where we balance the redox reaction with 2 electrons. So always remember, your cell potential refers to the balanced redox reaction, but it is not affected by the way you balance your redox reaction, in particular, your electron number. Okay, so let's try solving this problem. So we have the hydrogen-oxygen fuel cell. So it says it's a voltaic cell. Remember, voltaic or galvanic cell is a cell that gives a positive cell potential. So we expect to get a positive cell potential in this problem. So we have the reaction, and we have the delta H naught F and the delta S naught F of the reactants and the product. So it means that we need to get delta H naught reaction first. So we need to get delta H naught reaction and delta S naught reaction from the given table. From these two, we will get delta G naught reaction. And from our delta G naught reaction, we should be able to get our standard cell potential. So we need to go back to our formula, which is the summation of the delta H naught of formation of our products multiplied by their corresponding coefficients minus the summation of the delta H naught F of our reactants multiplied by their corresponding coefficients. Okay, so we have liquid water as our product. So that would be negative 285.8 kilojoules per mole. And that's it, because the reactants are reference elements. So this summation is equal to 0. So this is our delta H naught reaction. Now for our delta S naught, we have the synonymous formula, or the counterpart for entropy. But what we have is absolute entropy of formation. So for water, we have 109.6 joule per mole per Kelvin. So that's 2 times 109.6 joule per mole per Kelvin minus for hydrogen gas, that's 2 times 130.7 joule per mole per Kelvin plus, so 1 for oxygen, it has a coefficient of 1. So we simply add 205.1 joule per mole per Kelvin. Okay, so now our delta S naught reaction is, so that's 2 times 109.6 minus 2 times 130.7 plus 205.1. So we get negative 247.3 joules per mole per Kelvin. So now we will use, the next step is we will use our Agatha's equation to get delta G, or the standard Gibbs free energy change of our reaction. Now, all of these are in standard state. And again, it is typical to set the temperature at 25 degrees Celsius or 298.15 Kelvin. So this is the temperature value that we will use. So we have negative 285.8 joule or kilojoules per mole. We will convert this to joules. And then we have minus 298.15 Kelvin times negative 247.3 joules per mole per Kelvin. So our Gibbs free energy change for this reaction is equal to So we have negative 212,667.505 joules per mole. So now we can compute for the standard cell potential. So this is equal to negative delta G naught reaction over N times Faraday's constant. Okay, but now we need to get the electron number. So we need to balance the reaction, right? So how do we balance the reaction? How do we determine which is oxidized and which is reduced? You have to be able to know that. Just watch the video that I posted on balancing redox reactions. Okay, so the one that is oxidized is hydrogen. So in our anode, our half reaction is H2 gas forming water liquid plus 2 electrons. And then in our cathode, we have oxygen gas being reduced. So we have O2 being formed into water as well. But this one is gaining 2 electrons. So this should actually be 2H2. Yes. Yeah. This one should be H2 and only 1 electron there on the product side. So this will be multiplied by 2. Is that correct? Okay. This one, this must be 1/2. Okay, plus 2 electrons. Okay. No. Wait. Let me organize my thoughts. Okay. Let's do this step by step. So hydrogen and oxygen have oxidation numbers of 0. Both are 0. Here we have oxygen with an oxidation number of -2 and hydrogen with an oxidation number of +1. So we see oxygen is the one reduced and hydrogen is the one oxidized. So we have H2 and H2O as the product in our anode half reaction. And we have O2 and H2O as the product in the cathode half reaction. So we need to balance the oxygen here, and oxygens are actually balanced by water. So I will add water, one water molecule here, and one two H plus to balance the added hydrogens. So now I have four hydrogens, and one oxygen for each side. That means there must be 2 electrons here to balance the charge or to make the charge equal to 0 because the total charge on the reactant side is 0. So our anode half reaction is good. Let's go to the cathode half reaction. Here, we are missing one more oxygen. So I place a coefficient of 2 here for water. And that means I need to introduce 4H plus on the reactant side. And this means I have to add 4 electrons here. And then I need to multiply this by 2 so that the number of electrons is equal. That means there are 4 electrons involved. And by simplifying, so we have 2H2. That's 2 water. And then we have O2 plus 4H plus. And then we get here 2 water plus 4H plus 2 water. And to simplify, we can cancel out the H plus and 2 water. We get the overall reaction. So our balancing is correct. And here we see that there are 4 electrons involved. So that's our electron number. So now we have negative 212,067.505 joules per mole divided by 4 times 96,485 coulombs per mole. So this is equal to that's 4 times 96,485. Okay, so we get negative 0.549 volt. I forgot the negative sign in our formula. So delta G naught reaction is negative, then it's negative of delta G naught reaction. Okay, so see there, I got a negative answer, but we know that it should be positive because the cell is described as a voltaic cell. So going back, I saw that I missed that negative sign in the reaction. Okay, so that's how we always check our final answer if it makes sense. So we get a standard cell potential of positive 549 volt. Okay, it's positive because it's a voltaic cell. Okay. Now, just remember, class, that in our study of thermodynamics from Hess's law, we know that if we add our thermochemical equations, we simply add their delta H, delta S, or delta G values, right? But that doesn't apply to our redox reactions, which means if we add two redox reactions, we do not simply add their cell potentials to get the cell potential of the resulting reaction. So as an example, we have here, just to simplify things, we will just consider half reactions. So we have two reduction half reactions here. So from iron 2 to solid iron and from iron 3 to iron 2. So we are interested in getting the standard cell potential of this reduction half reaction, which is that of iron 3 to solid iron. And this one is the resulting reaction if we add these two. But again, the standard cell potential for the resulting reaction is not the sum of these two standard cell potentials. But there is a way for us to determine the cell potential of this overall reaction. And that is by using the formula for delta G. So what you need to do is first to get the delta G naught for each reaction, okay? Add the two reactions, so you will add the two delta G naught values, right? That will give you the delta G naught for the resulting reaction. From this, you can get your cell potential. So let's do that. Let's go for the first reaction here, which is that of iron 2 to solid iron. So delta G naught for this reaction is negative 2 times Faraday's constant, 96,485 coulombs per mole, times the standard cell potential, negative 0.440 volt. So that is equal to 84,906.8 joule per mole. So we get a positive value because the standard cell potential is negative. Then for the second reaction, that is the reduction of iron 3 to iron 2. So the delta G naught for this reaction is negative 1 times 96,405 coulombs per mole times that standard cell potential, 0.771 volt. So we get negative 74,389.935 joules per mole. So again, we add the two half reactions. We get this overall, right? So we can get delta G naught for this overall reaction, which is this plus 84,906.8. So that is 10,516.865 joules per mole. So now we can get the value of the standard cell potential, which is 10,516 negative 10,516.865 joules per mole over 3. So there are 3 electrons involved times 96,405 coulombs per mole. So that's negative of the delta G divided by 3 times 96,485. So we get negative 0.0363 volt. So notice that it's not the sum of negative 0.440 and 0.771. Okay? This is how we consider the combination of our redox reaction. So this one, our example was just involving half reactions, but the same principle is applied for redox reactions. Okay, now, since we've already touched delta G in connection with our electrochemical cells, in particular voltaic cells, then we can now dive deeper into the spontaneity of our redox reactions. So from our formula, connecting electrochemistry and thermodynamics, we see that if we have a cell potential that is positive, we get a negative delta G value. This means that our redox reaction as written, okay, whatever reactants you have and whatever products you have, so as it is written, then the forward reaction is spontaneous. Okay? And if you get a cell potential that is negative from this equation, it tells us that the cell potential, or sorry, the delta G must be positive. Okay, which means the reaction occurs spontaneously in the reverse. So you have the reaction written, right? The reactants and the products. If the cell potential is negative, then the forward is non-spontaneous, but the reverse is spontaneous. So if you fix the setup such that your products will be the reactants and the reactants will be your products, then you have a spontaneous redox reaction. Again, if cell potential is 0, the reaction is at equilibrium for the stated conditions. Now, notice class that our qualifier here, or our parameter, is not exactly standard cell potential, but what we have is is just simply cell potential. So you might be asking, what is the difference between the two? What do you think is the difference? If you thought concentrations of the ions, you are correct. So again, this standard cell potential means that the concentrations of the ions are 1 molar. If we are talking about simply cell potential without that degree or not there as the subscript, that means you are not in a standard state. If you have gases in the reaction, then the pressure of the gas is not 1 atmosphere. If you have aqueous ions, then the concentration is not 1 molar. So just remember, class, your parameter is cell potential, not just standard cell potential. It must be cell potential. Okay, so for example, class, will aluminum metal displace copper 2 ions from aqueous solution? Now this question is incomplete. So we will be considering standard state. Okay, so since we are considering standard state, then we go back to our equation of delta G naught equals negative NF E naught cell. So again, if you have a positive delta G, it means the process is non-spontaneous. If you have a negative delta G, the process is spontaneous. So the condition or the scenario is you have aluminum metal displacing copper ions in solution. Okay, so I went ahead by writing the balanced redox reaction, but just to practice, so your cathode here is the one that is reduced, which means that is copper. So you have copper 2 plus 2 electrons forming your solid copper. And your anode is the one that is oxidized. So you have solid aluminum forming aluminum ion plus 3 electrons. And then again, the number of electrons must be equal for both half reactions. So we have this balanced redox reaction. Okay, so for our cathode, the standard reduction potential is equal to, so that's copper 2, right? That's positive 0.340. And for our anode, that would be aluminum, which is negative 1.676. Now notice class, if we multiply the half reaction by a certain coefficient, we do not multiply the standard reduction potentials. Again, this is because your cell potentials or electrode potentials are intensive properties, okay? They do not depend on the stoichiometry or how you write your balanced redox reaction. So we do not multiply this cathode potential and anode potential by the coefficient that we used to balance the electrons. So we retain these values, okay? So that would be cathode minus anode. So that's 0.340 minus negative 1.676. So we get 2.016 volts. Okay, this is the standard cell potential. We get a positive standard cell potential. And according to our equation, a positive standard cell potential will give a negative standard Gibbs free energy change, which means this process is spontaneous. So if I have a solution of copper 2 ions, so again, copper 2 ions are color blue. So the solution is blue, okay, because of the copper 2 ions. And then if I place an aluminum metal, let's say aluminum foil, in this solution of copper 2 ions, then you will observe the aluminum metal, it will dissolve. So it will disappear. Like your aluminum foil will disappear. And you will also see the color blue disappearing. Okay? The color blue will disappear because you are consuming your copper 2 ions. And you will eventually observe the formation of solid copper, which is color red. So it's described as brick red. And you will observe the formation of your precipitate. Okay, so it's spontaneous. Okay. Now, it is also important to note the behaviors of metals in acids. And this actually has a lot of applications or implications in our daily lives. So if we consider, again, acids, so there is your hydrogen ion is involved. We have here our metals. Of course, we start with a solid metal. And of course, since we start with a solid metal, it must undergo oxidation. Okay, so any metal will undergo oxidation. And then you have the reduction of your hydrogen ions in an acidic solution. So that will generate hydrogen gas. So your overall reaction will be this. So you have your solid metal plus your acidic solution producing the ion of your metal plus hydrogen gas. So since the reaction produces hydrogen gas, you will actually observe bubbles forming in your test tube. For this general reaction, then we have here a formula for our standard cell potential, which is the potential of your hydrogen gas electrode, because that's the reduction. So this is your cathode, minus the standard electrode potential of your anode. So the one containing your metal. Again, this one is 0 volts. Why? This is just your standard hydrogen electrode reversed. Diba si standard hydrogen electrode, it's set as an anode, so oxidation reaction siya. So if you reverse it, then siya yung nasa cathode na. So reduction naman yung reaction na nangyayari. So it's still 0 volts. Wala siyang value. Even if you invert sign, wala namang sign ng 0, diba? So it's still 0 minus the standard electrode potential of your metal electrode or yung nasa anode natin. So this gives us a negative standard electrode potential. Negative of the standard electrode potential, I mean. So again, we are talking about behaviors of metals in acids, diba? So since we have this formula for the standard cell potential of an acid reacting with a metal, then this means that if we have, let's say, magnesium, okay, magnesium metal dissolved in acid, we know that it will dissolve in acid. It will react with acid. Why? Because if you look here, its standard electrode potential or standard reduction potential is negative 2.356. So plug this into our formula, that's negative of negative 2356, that will give us a positive cell potential. Again, if your standard cell potential is positive, the reaction is spontaneous. So that means magnesium metal will react with acid. So it will dissolve with acid, producing hydrogen gas. But for example, we have here silver. Okay, silver. So if you place silver in an acid, such as hydrochloric acid, it will not react because it has a positive standard electrode potential. So negative of positive 0.8 is a negative value, so the reaction is not spontaneous. However, this is only true if we have acids such as HCl, HBr, HI. These are acids that produce hydrogen ions or release hydrogen ions in solution, right? So the oxidizing agent here is the H+. However, we also have acids, particularly strong acids, such as nitric acid, that have or possess a stronger oxidizing agent than the H+ that they release in solution. And what is that stronger oxidizing agent? It's the nitrate. So nitric acid dissociates into H+ and NO3-, right? H+ is an oxidizing agent. However, it's not strong enough to react with your silver metal, according to what we just learned. However, nitrate, also an oxidizing agent, is actually able to oxidize your silver metal. So if you look here in our table, nitrate is found above silver. Okay, so it has a more positive standard electrode potential, which means if we react solid silver with nitrate, like from nitric acid, then that means our standard cell potential will be 0.956 minus 0.800, which will give us positive 0.156 volt, a positive standard cell potential. This reaction is spontaneous. Okay, silver will not react with HCl because this reaction of hydrogen ion to hydrogen gas is lower relative to your silver half reaction. Okay? So this means, class, anything that is lower. So for example, if I have solid aluminum dissolved in a solution of lead 2, for example, then that would be, so that would be spontaneous, right? Because that will give me still a negative cell potential. Because look, if I dissolve solid silver in a solution of lead 2 ions, the standard cell potential will be negative 1.676 minus negative 0.125. That will give, oh, okay, that's non-spontaneous. Okay, that's non-spontaneous. So aluminum solid cannot displace lead 2 ions in solution because you get a negative standard cell potential. But solid lead can displace aluminum 3 plus ions in solution because, okay, what will happen here is that you have, ay hindi, baliktad pala class. Baliktad. Balik tayo. Solid aluminum in a solution of lead 2 ions, okay? So can aluminum replace or displace lead 2 ions in solution? So our reduction half reaction is this one, that's negative 0.125 minus our oxidation half reaction is the reverse of this. Diba, ma-oxidize yung aluminum. So that would be minus negative 1.676. Okay, there you go. The standard cell potential is positive, which means solid aluminum can displace lead 2 ions. That's correct, right? If I have solid aluminum and lead 2 ions in solution, so the products will be solid lead plus aluminum ions. Okay. So the reduction is that of lead 2 ions. So reduction, that is the cathode. So that's negative 0.125 volt minus the anode reaction is that of aluminum. So that would be anode, no? So it's the reverse of this one. So minus negative 1.676. Ayun. So it's 1.551 volt. Okay, so this is spontaneous. Aluminum can spontaneously displace lead 2 ions. But solid lead cannot displace aluminum ions. Is that correct? So that would mean if aluminum is displaced, then this reaction is taking place. So that is our reduction half reaction. So negative 1.676 minus the anode reaction, which is the reverse of this, negative 0.125. That will give you a negative standard cell potential. So if the reverse happens, solid plus, which is actually just the reverse of this one. If you reverse this, your standard cell potential will just be negative 1.551 volt. And it's non-spontaneous. But if you reverse it, it will be spontaneous in the indicated direction. Okay? So any solid here in the hierarchy, any solid can displace an ion above it. So calcium can displace iron 2, lithium can displace lead 2, and so on. But tin here cannot displace aluminum 3. Iron here cannot displace lithium, and so on. Okay, so there's also this concept of hierarchy, okay, or the ability of metals to displace ions in solution. Okay. So now we go to the connection of electrochemistry and equilibrium. So we're finished with the connection of electrochemistry and thermochemistry. Let's go to equilibrium. Okay, so this one stems from the fact that we have this equation. Okay, And we also have this equation for delta G. Okay, notice the difference. Delta G naught is our Gibbs free energy change if your reaction is at equilibrium. But if your reaction is not at equilibrium, then we simply have delta G. Okay, and again, your Q defines which direction your reaction will proceed to so that it reaches a state of equilibrium. You remember? If Q is greater than K, then it will shift backwards. If Q is less than K, it will shift forward. And if Q is equal to K, then you are in a state of equilibrium, which means delta G is equal to 0. And we go back to this equation. This should be plus. Delta G equals delta G naught plus RT ln Q. Okay, now again, from what we learned, standard cell potential is equal to delta G naught, right? So we have delta G naught is equal to negative NF standard cell potential, okay? Which means we can also define delta G equals delta NF E cell. This is our non-standard state. So if we replace delta G naught here, or delta G with NFE cell, again, the non-standard state, and delta G naught with negative NF E naught cell, plus RTL and Q, okay? And we divide the whole equation by negative NF. So we get E cell equals E naught cell plus minus. So this becomes minus RT over NF ln Q. Okay, so we have this relationship with of cell potential with equilibrium. Now, this is actually what we call the Nernst equation. Okay, so this was proposed in 1889 by Walther Nernst. And this is where we see the concentration dependence of our cell potential. Okay. Previously, class, we learned that if your reaction is at equilibrium, your E cell is equal to 0. Your Q is equal to K. So this equation is now reduced to E naught cell equals RT over NF ln K. So this is at standard state, and your reaction is at equilibrium. So R here is defined as your universal gas constant in joules per mole per Kelvin. Temperature will be defined as 298.15 Kelvin. And of course, we have Faraday's constant, which is 96,485 coulombs per mole. If we plug in these constants, we actually get this value, and the remaining variable is just the electron number. So this is the simplified equation for the relationship, or the equation showing the relationship between standard cell potential and your equilibrium constant. So are you seeing the connection here? If your reaction is at equilibrium, cell potential is 0, but your standard cell potential is not equal to 0. And standard cell potential is connected to the equilibrium constant. If it's simply cell potential, a non-standard cell potential, it's not related to your equilibrium constant, but to your Q, or the reaction quotient. Okay? Now, again, class, we saw what is called the Nernst equation, right? This is your Nernst equation. Okay. This Nernst equation shows the relationship of cell potential with concentration. Okay. So, Cell potential as a function of concentration, again, is displayed by the Nernst equation. So if we have this redox reaction, you have copper 2 ions with a concentration of 2 molar and zinc ions with a concentration of 0.1 molar. These are non-standard states. You will measure a different cell potential. It's not the standard cell potential anymore. Okay? So again, this relationship is expressed in your Nernst equation. Okay? So if you try to plot RT over NF, then that would be Ln zinc over concentration of copper 2. Okay. If you try to plot the ratio of the concentrations of your ions on the x-axis versus the cell potential, you actually get this line with a negative slope. Now notice in this plot, it's in the logarithmic form. Most analytical chemists actually transform this into the logarithmic form. So that requires a factor of 2.303. So that's RT over NF, logarithm of zinc ion concentration over copper ion concentration. Okay. So it's a straight line with a negative slope because this equation is the slope-intercept form of a line. You have cell potential as your y, negative 2.303 RT over NF as your slope, this logarithmic term as your x, and your standard cell potential as your y-intercept. And this is actually another way of evaluating standard cell potentials without using your reference electrode. Because if you perform this, if you measure cell potential with different concentrations of your reactants and products, you get this line and just get the y-intercept. Your y-intercept will give you your standard cell potential. But of course, this is more prone to errors because you are performing multiple measurements. There. So this is the function of your Nernst equation. Okay. So I guess I will end the recording here and then we will continue with some exercises using this equation. So your standard cell potential and equilibrium constant and using our Nernst equation. Okay, so this ends this recording and hopefully you are slowly developing appreciation for electrochemistry.